Look at any object near you. A cup, a book, your own hand. It has properties, doesn't it? A definite position, a definite color, a definite shape. And you assume, without ever thinking about it, that those properties are simply there, that the cup is sitting in its definite place, with its definite color, whether or not anyone is looking at it. Turn away. Leave the room. Close your eyes, and surely the cup remains exactly as it was, definite and real, and there. This is perhaps the most basic assumption you make about reality. An assumption so deep you have probably never once questioned it, that the world is definitely there, with definite properties. Whether or not anyone observes it, the moon is in the sky even when no one is looking at it. Things are simply, solidly, definitely real. And here is one of the most disturbing facts in all of modern science. That assumption, that bedrock, common sense, seemingly unquestionable assumption, has been proven false, not as a matter of speculation or philosophy or interpretation, but as a matter of hard experimental fact, demonstrated in laboratories, confirmed again and again with ever greater rigor, and honored just recently with the Nobel Prize in physics. The universe the experiments show is not what physicists call locally real. The deep assumption that objects have definite properties sitting there, whether or not they are measured, combined with the equally reasonable assumption that nothing can influence anything else faster than light, simply cannot both be true. The world does not work the way our deepest intuition insists it must. And the experiments that proved this are some of the most careful and conclusive ever performed. Now, before we go a single step further, I need to be very clear about something, because this idea is one of the most misunderstood in all of science, and the misunderstanding can turn a profound discovery into a source of needless terror. This does not mean that nothing is real. It does not mean the world is an illusion, or that you do not exist, or that reality is a dream. The cup is still there. You are still real. The world is solid and genuine and exactly as present as it has always been. What the experiments overturn is not the reality of the world, but one very specific assumption about how that reality is put together. A subtle and technical assumption that turns out to be false, even though the world remains entirely real. The distinction is everything, and we will return to it carefully. Because getting it right is the difference between understanding one of the deepest truths physics has ever uncovered and frightening yourself with a misreading of it. Hold on to that promise as we go, because the journey ahead will take us through some genuinely vertiginous territory. And it is easy, in the middle of it, to feel the ground give way. There will be moments when the implications seem to threaten the solidity of everything, when the idea that things might not be definitely there, until measured, can feel like a trapdoor opening beneath reality itself. But every time we reach such a moment, we will steady ourselves on the firm distinction between what the discovery actually says and what it is so, often wrongly taken to say. The real discovery is profound and strange, but it is not the nightmare that the misreadings conjure. It does not dissolve your world. It does not make you a ghost in an unreal dream. It reveals instead that the solid and dependable world you live in rests on a foundation far subtler and more wonderful than anyone suspected. And that is a thing to marvel at, not to fear. And it is worth saying, right at the outset, why this is worth your attention at all. Why you should care that some assumption called local realism has failed. You should care because this is not a small technical result tucked away in a corner of physics. It is a discovery about the deepest nature of the reality you are part of. about what the world fundamentally is beneath the surface of appearances. It touches the most basic question a curious mind can ask. Is the world really there? Definitely, in the way it seems, when no one is looking. For all of human history, that question belonged to philosophers and dreamers, with no way to answer it. And in our time, astonishingly, it became a question that could be settled in a laboratory, and was. To understand what the experiments found is to understand something true and profound about the very fabric of existence, and that is worth a little vertigo along the way. Tonight, we are going to journey into one of the strangest and most profound discoveries in the history of science, the discovery that the universe is not locally real. We are going to start with the comfortable, common-sense picture of reality that everyone carries, the assumption that things are definitely there, with definite properties. Whether or not we look, we are going to watch as quantum physics challenged that picture in the most unsettling way, suggesting that particles do not have definite properties until they are measured. We are going to follow the greatest scientific mind of the 20th century, Einstein himself, as he fought against this idea, insisting that reality must be more sensible than the quantum theory suggested. We are going to meet the quiet genius who found a way to settle the argument, not with philosophy, but with an actual performable experiment, a way to put the very nature of reality to the test. We are going to witness the verdict of those experiments, a verdict that shocked the world and earned a Nobel Prize. And we are going to sit carefully and without fear with what it all means, and with what it does not mean, arriving at a picture of reality far stranger and far more wonderful than the common-sense world we thought we lived in. But to understand what was overturned, we first have to understand the assumption itself, the deep and reasonable picture of reality that almost everyone holds without realizing they hold it. Because it is only by seeing clearly what we assume that we can appreciate how astonishing it is that the assumption turned out to be wrong. The assumption has two parts, and both of them feel like simple common sense. The first part is what physicists call realism. Realism is the idea that objects have definite properties, whether or not anyone is observing them. A coin lying in a drawer is either heads or tails, definitely one or the other, even though no one is looking at it. A particle has a definite position and a definite motion, even if we do not know them. The properties of things are real and definite, and there, sitting in the world, independent of whether anyone measures them or looks at them. This seems almost too obvious to state. Of course, the coin is heads or tails in the drawer. Of course, things have definite properties, whether we look or not. What else could possibly be the case? To deny this seems absurd, almost insane. And yet, as we will see, it is precisely this innocent-seeming assumption that the universe forces us to question. Consider how completely this assumption governs the way you move through the world. When you put your keys in your pocket, you do not believe they hover in some undefined state until you reach for them again. You believe they are simply there, definitely in your pocket, the whole time. When you park your car and walk away, you do not imagine it dissolving into a haze of possibilities. You assume it sits exactly where you left it, definite and real, whether or not anyone is looking. Every plan you make, every expectation you hold, rests on the silent assumption that the world has definite properties continuously, that things are what they are, independent of observation. This is not a belief you arrived at through reasoning. It is the default setting of the human mind, the framework inside which all your thinking about the physical world takes place. It is so fundamental That to question it feels almost like vertigo, like asking whether the floor will hold. The philosopher's classic way of putting it is to ask whether the moon is there when nobody is looking. To anyone with common sense, the question seems almost insulting. Of course, the moon is there when nobody looks at it. It does not wink out of existence the moment everyone turns away and wink back when someone glances up. It is a real, solid, definite object, hanging in space, with a definite position and a definite shape, entirely independent of whether any eye is upon it. This is realism in its simplest form. The conviction that the world has a definite existence and definite properties, whether or not it is observed, and it is so deeply woven into our thinking that it seems less like an assumption and more like a precondition for sanity. And yet, it is exactly this conviction, at the level of the smallest things, that the experiments call into question, not for the moon as a whole, but for the particles from which the moon and everything else is built. The second part of the assumption is what physicists call locality. Locality is the idea that things can only be influenced by their immediate surroundings, and that any influence travels through space at a limited speed, no faster than the speed of light. If something happens over here, it cannot instantly affect something far away over there. For one thing to influence another, some signal, some force, some effect has to travel across the space between them, and that traveling takes time, and it cannot happen faster than light. This, too, seems like simple common sense, and it is woven deeply into our entire understanding of physics. Nothing happens instantaneously across a distance. To poke something far away, you have to reach it, and reaching takes time. The world is local. Effects propagate from place to place at finite speed, and what happens in one location cannot magically, instantly determine what happens somewhere far off. Put these two reasonable assumptions together, realism and locality, and you have what physicists call local realism. It is the picture of reality that almost everyone holds, the picture that feels like nothing more than basic sanity. Objects have definite properties, whether or not we look at them, and nothing can influence anything else faster than light. The world is made of definite things sitting in definite states, and they affect one another only through influences that travel across space at limited speed. This is the common sense view of reality, the one built into our intuitions, the one that Einstein himself held and defended, the one that seems so obviously true that questioning it feels like questioning whether the ground is solid. And it is this entire picture, this combination of realism and locality, that the experiments have shown cannot be true. Notice how deeply these assumptions run, how much they feel like preconditions for the world making any sense at all. If objects did not have definite properties when unobserved, what would they be? A foggy cloud of maybes, a smear of possibilities, somehow not quite settled into reality until someone checked. That sounds like madness, like the world is playing some kind of trick. And if influences could travel faster than light, instantly, across any distance, then the whole orderly structures of cause and effect, of things affecting their neighbors in a sensible sequence, would break down, replaced by a reality where distant things are mysteriously, instantly linked. Both alternatives seem not just wrong, but almost unthinkable. And that is exactly why the discovery is so profound and so unsettling. Because the universe, it turns out, forces us to accept at least one of these seemingly unthinkable things. Locality, like realism, is something we rely on constantly without ever naming it. When you flip a switch and a light comes on, you assume something traveled from the switch to the light through the wire. taking some small amount of time, however brief. When you call someone far away, you assume the signal crossed the distance between you, carried by something moving through space at a finite speed. Nothing in your experience ever happens by instant influence across a gap. Everything that affects something else does so by reaching it, by sending some signal or force across the intervening space. And that reaching always takes time. The idea that you could affect something far away instantly, with no signal crossing the space between, with no delay at all, strikes us as not just impossible, but almost magical, the stuff of fairy tales. We are deeply, instinctively committed to the locality of the world. And modern physics, before quantum mechanics complicated the picture, had elevated this instinct into a firm law. The discovery that nothing can travel faster than light, one of the cornerstones of Einstein's own work, seemed to seal locality into the very structure of reality. If no signal, no influence, no information can outrun light, then surely nothing can instantly affect anything across a distance. The speed of light sets a strict limit on how fast any influence can propagate. Locality was not just common sense. It was, it seemed, a deep principle of physics, confirmed and enshrined. To give it up would mean accepting that reality contains instant connections across space, influences that ignore the cosmic speed limit, exactly the spooky action that Einstein found intolerable. And so locality, like realism, stood as one of the twin pillars of the sensible world, seemingly beyond question, until the experiments showed that the two pillars could not both stand. For a long time, of course, no one imagined that local realism could ever be tested. It seemed like a philosophical assumption, a matter of common sense, not the kind of thing you could put in a laboratory and check. How could you possibly perform an experiment to determine whether objects have definite properties when no one is looking? The very question seems to defeat itself, since to check the properties you would have to look, and then someone is looking. It appeared to be exactly the sort of deep assumption about reality that lies forever beyond the reach of experiment, a thing you simply had to assume one way or the other. And for the first decades of the quantum era, the debate over whether the world was locally real was treated as just that, a matter of philosophy and taste, an argument that could never be settled by doing an experiment that, as we will see, turned out to be wrong, and the person who showed it was wrong, performed one of the greatest feats of insight in the history of physics. But to understand his breakthrough, we first have to understand the strange new physics that called local realism into question in the first place, the physics of the quantum world. In the early 20th century, physicists probing the world of the very small, of atoms and particles and light, found something deeply strange, something that did not fit the comfortable picture of local realism at all. According to the new theory they developed, quantum mechanics, the tiniest constituents of reality do not behave like little definite objects with definite properties. Instead, before they are measured, they seem to exist in a strange, blurry state of multiple possibilities at once, not here or there, but in a kind of haze spread across many possible values, not settled into any one definite property until the moment a measurement is made. A particle, according to the theory, does not have a definite position waiting to be discovered. Rather, it exists in a spread of possible positions, and only when measured does a single definite position appear. The same goes for other properties. The particle is, in a sense, undecided, a cloud of possibilities, until the act of measurement forces a single outcome into being. To feel how strange this is, contrast it with ordinary ignorance, because the two are easy to confuse and the difference is everything. Suppose I flip a coin, catch it, and cover it with my hand before either of us sees it. The coin is either heads or tails. It has a definite value, and we simply do not know which. That is ordinary ignorance, the everyday situation in which something has a definite property we happen not to have observed. Now, the quantum claim about a particle is not like this at all. It is not that the particle has a definite value we have not yet learned. It is that the particle has no definite value yet, that it genuinely exists in a blend of possibilities, in a state that is somehow all of them at once and none of them in particular, until measurement forces a single answer into being. The difference between not knowing a definite answer and there being no definite answer to know is subtle to state but enormous in meaning, and it is the very heart of what makes quantum mechanics so disturbing to common sense. Physicists have a name for this strange blended condition: superposition. A quantum system in superposition is not in one state or another, but in a combination of states, a genuine blend of possibilities. And the mathematics of quantum mechanics describes this blend with great precision and predicts with stunning accuracy the probabilities of the different outcomes that appear when a measurement is finally made. The theory does not merely tolerate this indefiniteness. It is built around it, and its predictions, confirmed to extraordinary precision in countless experiments, depend on taking the superposition seriously as a real feature of the world and not just a statement of our ignorance. The success of quantum mechanics is, in a sense, the success of taking indefiniteness seriously, of treating the haze of possibilities as something real rather than as a mere mask over hidden definite values. And that is precisely what made it so troubling, because it suggested that realism, the comfortable assumption that things have definite properties all along, might simply be false. This was a radical departure from everything that came before, and it is worth being careful about what it claims. It is not merely saying that we are ignorant of the particle's properties, that the particle has a definite position. We simply have not measured yet. It is saying something far stranger, that the particle genuinely does not have a definite position until it is measured, that the definiteness itself comes into being only at the moment of measurement, that before that moment there is no fact of the matter about where the particle is, only the spread of possibilities. The quantum description does not say we are missing information about a definite reality. It says the definite reality is not there yet, that it crystallizes out of a haze of potential only when a measurement occurs. This is such an alien idea that it is worth stating plainly just how much it asks of us. It asks us to imagine that at the deepest level, the world is not a collection of things with properties waiting to be observed, but something more like a field of tendencies, of potentials, of possibilities not yet realized, which become definite actualities only in the event of measurement. Reality, in this picture, is not a finished painting hanging on a wall, complete whether or not anyone looks. It is more like a painting that is, in some sense, still being painted at the moment of looking, the definite strokes appearing as they are observed. This does not match anything in our ordinary experience, where the world seems so obviously finished, so completely there, so independent of our attention. And that mismatch between the quantum description and our lived experience is exactly the puzzle that drove the whole debate that led Einstein to insist the description must be incomplete, and that ultimately could only be resolved by the experiments we will come to. It's important to stress that this strange picture was not adopted lightly. or for its own sake. Physicists did not embrace the indefiniteness of the quantum world because they found it appealing. Most of them found it deeply uncomfortable, and many, like Einstein, resisted it fiercely. They were driven to it by the sheer success of the theory, by the fact that treating the quantum world as a realm of genuine indefiniteness, of possibilities not yet realized, produced predictions of astonishing accuracy. Predictions confirmed in experiment after experiment to more decimal places than almost any other theory in the history of science. The strangeness was the price of that success. The theory worked better than anything before it, and it worked by taking the indefiniteness seriously. And so physicists were faced with a hard choice. Accept a picture of reality that defied common sense, or reject the most successful theory ever devised. It was this tension between the theory's success and its strangeness that set the stage for everything that followed. Now, a crucial clarification, because this is where misunderstanding creeps in. When physicists say measurement, they do not mean that a conscious human mind has to look. Measurement in physics means a physical interaction, an event in which the quantum system interacts with something larger, a detector, an instrument, the wider environment, in a way that produces a definite outcome. It has nothing to do with consciousness or human awareness. A measurement happens whenever the right kind of physical interaction occurs, whether or not any person is watching. The dramatic phrase, that things are undecided until you look, is a vivid shorthand, but the real meaning is about physical interactions producing definite outcomes, not about minds magically conjuring reality. The world is not waiting for human attention. It is the physics of interaction and measurement, not the gaze of an observer, that brings definite properties into being in the quantum description. Even with that clarification, the quantum picture was deeply unsettling because it suggested that the bedrock assumption of realism, the idea that things have definite properties, whether or not they are measured, might simply be false at the level of particles. And not everyone accepted this. In fact, one of the greatest scientific minds who ever lived found it not just unsettling but unacceptable, a sign that the quantum theory, for all its success, must be incomplete, must be missing something. He could not believe that the universe was really like this, that definiteness only appeared upon measurement, that reality was a haze of possibilities until observed. He famously expressed his discomfort with the idea that the universe was fundamentally governed by chance and indefiniteness, insisting that there must be a deeper, more sensible reality underneath, one in which things really do have definite properties all along. That man was Albert Einstein, and his objection to quantum mechanics would set the stage for one of the most important scientific arguments of all time. An argument that, decades later, would finally be settled by experiment. It is striking and a little poignant that the man who led this objection was the very same Einstein, who had himself overturned so much of classical physics, who had shown that time and space bend and stretch, that the universe was far stranger than the comfortable Newtonian picture allowed. Einstein was no enemy of strangeness. He had embraced and revealed more of it than almost anyone. And yet, when it came to the indefiniteness at the heart of quantum mechanics, the idea that reality might not be definite until measured, that chance might be woven into the foundation of things, he balked. He famously expressed his conviction that the universe must be more orderly than this, capturing his discomfort in the memorable remark that he could not believe the universe played dice with reality. He did not mean it lightly. It expressed a deep philosophical conviction that, beneath the apparent randomness of the quantum world, there must lie a definite, orderly reality, that the indefiniteness was a sign of our incomplete knowledge rather than a true feature of the world. This was not stubbornness or failure of imagination. It was a principled stand by one of the deepest thinkers who ever lived, rooted in a powerful intuition about what reality ought to be like. Einstein believed in a world that was definite and orderly and comprehensible all the way down, a world where things had real properties, whether or not we looked, where chance was a measure of our ignorance and not a feature of reality itself. The quantum theory threatened all of that, and Einstein, rather than simply accepting it, did what great scientists do. He formulated his objection as precisely and powerfully as he could, hoping either to find the flaw in the new physics or to force it to reveal its incompleteness. His objection was not a refusal to think but the opposite, a rigorous attempt to pin down exactly what was at stake. And in doing so, he set up the very question that Bell would later find a way to answer. Even in being ultimately proven wrong, Einstein's objection was enormously productive because it framed the issue so sharply that it eventually became testable. In 1935, Einstein, together with two colleagues, published a famous argument designed to show that quantum mechanics could not be the complete story. The argument focused on a particularly strange quantum phenomenon, one that would become central to everything that followed: the phenomenon of entanglement. Entanglement occurs when two particles are created, or interact in such a way that their properties become linked, correlated, bound together, so that measuring one tells you something about the other, no matter how far apart they have traveled. You can prepare a pair of entangled particles, send them to opposite ends of a laboratory, or in principle to opposite ends of the galaxy, and the quantum theory says that measuring one will instantly be correlated with the result of measuring the other, the two outcomes linked across any distance. Entanglement is worth dwelling on because it is the strange phenomenon at the center of this entire story, and it is genuinely unlike anything in ordinary experience. When two particles become entangled, the quantum theory does not describe them as two separate things, each with its own state. It describes them as a single, unified system, a whole that cannot be fully broken down into independent parts, even when those parts are carried to opposite ends of the universe. Their properties are not merely similar or coordinated. They are bound together in a way that has no parallel in the world of everyday objects. Measure one, and the description of the other changes instantly, no matter how far apart they have traveled, as though the vast distance between them simply did not matter to the connection they share. This is what so disturbed Einstein, and what continues to astonish physicists today, that two particles, separated by any distance at all, can remain linked in this deep and unbreakable way, behaving as a single system across the void. An entanglement is not some rare laboratory curiosity. It is a pervasive feature of the quantum world, constantly occurring whenever particles interact, woven throughout the fabric of reality. Most of the time, in the warm and busy everyday world, the entanglement between particles is quickly scrambled and hidden by their interactions with everything around them, which is why we never notice it in ordinary life. But in the careful isolation of the laboratory, physicists can create and preserve entangled pairs and study the extraordinary correlations between them. And it is precisely these correlations that Bell realized could be used to test the deepest assumptions about reality. Entanglement is the thread that runs through the whole story, from Einstein's objection to Bell's insight to the Nobel-winning experiments, the strange quantum connection that, when examined closely enough, forced the universe to reveal that it is not locally real. Einstein seized on this. Here, he argued, was the problem with quantum mechanics laid bare. According to the theory, neither entangled particle has a definite property until it is measured. But the moment you measure one, the other is instantly correlated, even if it is light years away. If the particles really had no definite properties until measurement, then measuring one would have to somehow instantly influence the other across that vast distance faster than light to make their results match. And that, Einstein insisted, was impossible, a violation of locality, the principle that nothing can influence anything faster than light. He called it, dismissively, spooky action at a distance, and he refused to believe the universe worked that way. So Einstein proposed a sensible-sounding alternative, one that would save both realism and locality, one that would keep the comfortable common-sense picture of the world intact. What if, he suggested, the entangled particles actually did have definite properties all along, from the moment they were created? Properties that were simply hidden from us? In this view, there is no spooky action at a distance, no faster-than-light influence, because the correlation was set up in advance. The two particles are like a pair of gloves separated into two boxes and shipped to opposite ends of the world. Open one box, find a left glove, and you instantly know the other box contains a right glove, but nothing traveled between them. The gloves will simply left and right all along. In the same way, Einstein proposed, the entangled particles carried definite, predetermined properties from the start, hidden variables that the quantum theory failed to describe, and the apparent spookiness was just our ignorance of these hidden, predetermined values. The glove analogy is worth lingering on, because it captures exactly what Einstein wanted to be true. And it is so reasonable that it is hard to see how it could be wrong. Imagine a friend who owns a single pair of gloves, one left and one right. She puts each glove into its own box at random, seals them, and mails one box to you in your city and the other to a colleague on the far side of the world. Neither you nor your colleague knows which glove you have until you open your box. The moment you open yours and see a left glove, you know, instantly and with certainty, that your colleague's box, thousands of miles away, contains the right glove. Did your act of opening the box reach across the world and force your colleague's glove to become right? Of course not. The gloves were left and right all along from the moment they were boxed. The correlation was built in from the start, and your knowledge of the distant glove is simply a matter of logic, not of any influence traveling between the boxes. Nothing spooky happened. The definite properties were there, the whole time, merely hidden until revealed. This is precisely what Einstein believed must be happening with entangled particles. The correlations are real, he agreed, but they are explained, as with the gloves, by definite properties. Fixed at the moment the particles were created, properties that travel with each particle and are merely revealed, not created, by measurement. No spooky action, no faster-than-light influence, just predetermined values hidden from view until we look. It was an elegant, sensible, deeply appealing picture, and it preserved everything Einstein held dear about reality. That things have definite properties whether or not we measure them, and that distant things are not linked by instantaneous influences. The stakes, for Einstein, were nothing less than the sensibleness of the universe itself. The question of whether reality was the orderly, definite, locally connected place he believed it had to be, or the strange, indefinite, spookily connected place the quantum theory seemed to describe. He was betting on sense, on the gloves, on a world of hidden but definite values, and for decades, no one could prove him wrong. This was a brilliant and reasonable proposal, and it had enormous appeal because it would rescue the entire common-sense picture of reality. If Einstein was right, then particles do have definite properties whether or not they are measured. Realism is saved, and nothing influences anything faster than light. Locality is saved, and the strange correlations of entanglement are explained by ordinary, predetermined values just hidden from view. The quantum theory would not be wrong, exactly, but incomplete, a description that worked, but missed the deeper layer of definite hidden properties underneath. For decades, this remained a real and respectable possibility. Maybe the world was locally real after all, and quantum mechanics was simply an incomplete description of a deeper, sensible, definite reality. The question of who was right, Einstein with his hidden definite properties, or the quantum theory with its haze of indefiniteness, seemed to be a matter of philosophy, of taste, impossible to settle by experiment. Until a physicist named John Bell had one of the most brilliant ideas in the history of science, and showed that the question could, in fact, be answered in a laboratory. For nearly 30 years after Einstein's argument, the debate sat in a kind of stalemate. Einstein said the particles had hidden, predetermined properties. The quantum theory said they did not, becoming definite only upon measurement. Both views seem to explain the same experimental results equally well, since in the simplest entanglement experiments, where you measure both particles the same way, both pictures predict the same perfect correlation. Whether the correlation came from predetermined hidden values, as Einstein believed, or from spooky quantum indefiniteness, you got the same answer, so no experiment could tell them apart. The question seemed permanently beyond the reach of science, a matter for philosophers to argue about forever. Then, in 1964, an Irish physicist named John Bell asked a deceptively simple question that changed everything. What if, he wondered, you did not always measure the two entangled particles in the same way? What if, instead, you measured them along different angles, different settings, chosen independently at each end? And you did this many times, building up statistics about how often the results matched depending on the combination of settings. Bell worked through the mathematics, and he discovered something extraordinary. He found that if Einstein was right, if the particles carried definite, predetermined, hidden properties, and if no influence traveled faster than light, then the pattern of correlations across all those different measurement settings had to obey a strict limit. There was a ceiling, a mathematical bound, on how strongly the results could be correlated across the various combinations of angles. This bound came to be called Bell's inequality, and it held for any theory based on local realism. Any theory in which particles have predetermined properties and nothing travels faster than light. And here was the breathtaking part. Bell calculated what quantum mechanics predicted for the very same experiment. And quantum mechanics predicted correlations that exceeded the limit, that broke through the ceiling, that violated Bell's inequality. The two pictures of reality, which agreed perfectly, when you measured the particles the same way, made different predictions when you measured them along different angles. Local realism said the correlations could be no stronger than a certain amount. Quantum mechanics said they could be stronger, and the difference was not a matter of philosophy or interpretation. It was a difference in actual numbers, in measurable statistics, in how often the results would match in a real experiment. For the first time, the deep question of whether the world was locally real had been turned into something you could test. You could go into a laboratory, measure entangled particles along different settings, many times count up the correlations and see which prediction came true. If the correlations stayed within Bell's limit, Einstein was right and the world was locally real. If they exceeded it, local realism was false. It helps to have at least an intuitive feel for why measuring at different angles is the key that unlocks everything, even without the mathematics. Think again about predetermined properties, Einstein's hidden values. If each particle carries a fixed set of instructions, settled at birth, telling it how to respond to any measurement it might encounter, then when you measure the two particles along the same setting, they can be perfectly correlated because their instructions were coordinated in advance. So far, Einstein's picture works fine. But Bell realized that if you measure along many different combinations of settings and tally how the correlations behave across all those combinations, the predetermined instruction picture imposes a strict accounting, a limit on how the correlations at different angles can add up. The instructions are fixed in advance, so they can only do so much. There is only so far the correlations can go. If each particle is just following a pre-written script that cannot know what setting the other particle will face. Quantum mechanics, by contrast, predicts correlations that go further, that are stronger across those different combinations of angles than any pre-written script could produce. The entangled particles in the quantum picture are not following fixed individual instructions. They are part of a single connected whole, and when measured at different angles, they show a degree of coordination that no set of predetermined, independent instructions could ever match. So the different angles act like a kind of cross-examination of reality. Measured the same way, the two pictures tell the same story and cannot be told apart. But measured across many different angles, they diverge, and the pattern of correlations reveals whether the particles were following fixed local scripts as Einstein hoped, or whether something deeper and stranger was going on. Bell had found the question that would make reality show its hand, and all that remained was to ask it. It is hard to overstate what a stunning achievement this was. Bell had taken a question that everyone assumed was pure metaphysics, a matter of taste and philosophy, forever beyond experiment, and shown that it was, in fact, an experimental question with a definite answer waiting to be found. He had found a way to interrogate reality itself, to put the deepest assumption about the nature of the world, that things are definitely there, whether or not we look to a direct experimental test. It was as if someone had discovered a way to weigh a thought or measure a dream, to take in something that seemed utterly beyond the reach of science and bring it firmly within it. What makes Bell's achievement even more remarkable is its sheer unexpectedness, the way it found a crack of testability in a question everyone had assumed was sealed shut. For decades, the brightest minds in physics had treated the Einstein-Bohr debate as fundamentally unresolvable by experiment, a clash of interpretations that the data could never adjudicate, since both sides predicted the same results for the experiments anyone had thought to do. The assumption that it was untestable was nearly universal, and then Bell, by the simple but profound move of asking what happens when you measure at different angles rather than the same one, found the hidden seam where the two pictures diverge, the one place where they make different predictions, the crack through which experiment could finally reach. It is the kind of insight that, once seen, looks almost obvious, and yet no one had seen it for 30 years. That is the mark of true genius, to find the simple question that unlocks what everyone else believed was locked forever. And Bell's insight has a beautiful quality of fairness to it, a kind of intellectual honesty built into its very structure. He did not design a test rigged to give the answer he preferred. He found a genuine, neutral question whose answer would favor whichever picture was actually true. If local realism were correct, the experiments would vindicate it, and Einstein's hopes would be confirmed. If quantum mechanics were correct, the experiments would show that instead. The test did not presume the answer. It created a fair contest and let reality decide. This is science at its purest, the construction of a question that nature itself can answer without bias, whose outcome is determined not by the preferences of the questioner, but by the way the world actually is. Bell built the stage and let the universe speak, and that impartiality is part of what makes the eventual verdict so compelling and so impossible to dismiss. The nature of reality was no longer just a topic for armchair argument. It was a number you could measure. All that remained was to actually do the experiment, to prepare the entangled particles, measure them along the different settings, and let the universe deliver its verdict. And when physicists finally did, the answer was as clear as it was shocking. Think about what was truly at stake as those first experiments were prepared, because it is rare in science for a single measurement to carry such weight. This was not a test of some particular theory's fine details. It was a test of the very nature of reality, a chance to determine, by experiment, whether the world is the definite, locally connected place common sense insists upon, or something far stranger. The outcome would vindicate either Einstein, the towering genius who believed in a sensible underlying reality, or the quantum theory, with its haze of indefiniteness and its spooky connections. Whole world views hung on the numbers that would come out of those detectors. Few experiments in the history of science have been freighted with such deep significance. The answer to a question that humanity had asked, in one form or another, since the dawn of philosophy. Is the world really there, in the way it seems when no one is looking? And now, at last, the universe was about to answer. The anticipation was not, of course, felt by the wider world, which knew nothing of these experiments with entangled particles. It was felt by the small community of physicists who understood what was being tested, who grasped that a profound question about reality was about to be settled in a laboratory. For them, the running of these experiments was a moment of extraordinary tension and importance, the culmination of decades of debate, the point at which the universe would finally render its verdict on a question that the greatest minds had been unable to resolve by argument alone. And when the results came in and the inequality was violated and local realism fell, those who understood knew that something momentous had happened, that one of the deepest questions about the nature of existence had been answered, and that the answer was not the one common sense would have chosen. The first serious experiments came in the early 1970s, when a physicist named John Clauser, building on Bell's work, actually built an apparatus to test the inequality. It was painstaking, difficult work, generating pairs of entangled particles of light, photons, sending them to detectors set at different angles, and measuring the correlations between them over many thousands of runs. The technology of the time was crude by today's standards, the signals faint, the work slow and demanding. But the result came through. The correlations violated Bell's inequality. They exceeded the limit that local realism allowed. They matched, instead, the prediction of quantum mechanics. The first experimental verdict was in, and it sided with the quantum theory against Einstein's common sense picture. It is worth appreciating the courage it took to do this work at all in those early days, because the question was not considered respectable. Many physicists of the time regarded the whole matter of whether the world was locally real as idle philosophy, not proper physics, a question best left alone by anyone who wanted a serious career. To devote real effort and real laboratory resources to testing it was, in the eyes of some, a waste of time at best and a mark of eccentricity at worst. Clauser later recalled being warned that pursuing such questions could be harmful to a young physicist's prospects. And yet he did it anyway, driven by a genuine desire to know, building his apparatus, and running his experiment in the face of skepticism, because the question mattered to him more than the disapproval. There is something admirable in that, in the willingness to take seriously a question that others dismissed, to insist that it could and should be tested, and to do the difficult work of testing it, regardless of fashion. And the fact that the question was testable at all was, to many, the real surprise. Before Bell, the dispute between Einstein and the quantum theory had seemed permanently stuck in the realm of philosophy, the kind of thing reasonable people could argue about forever without resolution. Bell's insight had quietly changed that, but it took experimentalists like Clauser to prove, in practice, that the change was real, that you really could go into a laboratory and put the nature of reality to the test. Each experiment that violated the inequality was not just a data point against local realism. It was a demonstration that the deepest questions about reality were not forever beyond science's reach, that human ingenuity could find ways to interrogate even the most fundamental features of existence. The early experiments were the proof of concept for one of the most remarkable expansions of scientific reach in history, the moment when the nature of reality itself became a laboratory question. But a single early experiment, however suggestive, was not enough to settle a question this profound, and careful physicists worried about loopholes, ways that a clever local realist universe might still slip through and produce the results without truly violating local realism. Perhaps the particles somehow influenced each other through some subtle signal during the experiment. Perhaps the choice of measurement settings was not truly independent. Perhaps the detectors were only catching a biased sample of particles. Each of these loopholes offered a possible escape, a way that local realism might survive after all. And so, over the following decades, a series of ever more sophisticated and ingenious experiments set out to close them, one by one. It is worth appreciating just how seriously physicists took these loopholes, because their stubbornness about them is part of what makes the final verdict so convincing. A lesser standard of proof would have declared victory after the first experiments and moved on. But the question was so fundamental, the stakes so high, that physicists refused to accept the result until every conceivable way for local realism to survive had been hunted down and sealed off. The communication loophole worried that the two detectors, or the particles themselves, might somehow be exchanging information during the experiment, secretly coordinating their results through some ordinary signal. This could be closed by separating the detectors and switching their settings so fast that no signal slower than light could possibly cross between them in time. The detection loophole worried that the experiments were only catching a fraction of the particles, and that the missing ones might, if measured, restore local realism. This could be closed by building detectors efficient enough to catch nearly all of them. The freedom of choice loophole worried that the very choice of which settings to measure might somehow be correlated in advance with the particles' hidden properties. This could be addressed by choosing the settings using fast, independent, even cosmically distant sources of randomness. Each loophole was a genuine scientific worry, a real way that the comfortable picture of local realism might yet have survived, and closing each one required extraordinary experimental ingenuity. It took decades, because the technology had to be invented along the way. Detectors made more efficient, particle sources made brighter and more reliable, timing made more precise, distances stretched longer. And the truly decisive moment came when physicists managed to close the major loopholes all at once, in single experiments designed so carefully that local realism had nowhere left to hide. These loophole-free tests, achieved in the middle of the 2010s, were the capstone, the final sealing of every escape route, and they delivered the same verdict as all the experiments before them. Local realism was not merely unlikely, it was experimentally excluded, with every plausible objection answered. The thoroughness of the assault is part of why the conclusion is so secure, why it commands the confidence of the entire physics community, and why it was deemed worthy of the highest honor in science. In the early 1980s, the French physicist Alain Aspect performed a landmark series of experiments that dramatically tightened the test, including a version in which the measurement settings were changed so rapidly, while the particles were already in flight, that no signal, traveling at the speed of light, could have passed between the two detectors in time to coordinate the results. This addressed the worry that the particles were somehow communicating, by making such communication impossible unless it happened faster than light. And still, the inequality was violated. Still, the results matched quantum mechanics, not local realism. Then, in the following decades, the Austrian physicist Anton Zeilinger and others pushed the experiments further, still, across greater distances, with more rigorous controls, working to close every remaining loophole. By around 2015, so-called loophole-free experiments were achieved, tests so carefully designed that essentially every escape route for local realism had been sealed off at once. And the verdict, every single time, was the same. Bell's inequality was violated. Local realism was false. The universe was not locally real. For this body of work, this decades-long experimental assault on the deepest question about the nature of reality, John Clauser, Alain Aspect, and Anton Zeilinger were awarded the Nobel Prize in Physics in 2022. The prize was a formal acknowledgement, at the highest level of science, that the matter was settled, that the experiments had spoken clearly and repeatedly, that the common-sense assumption of local realism had been definitively ruled out by experiment. This was not a fringe result, not a contested interpretation, not one team's controversial claim. It was the considered verdict of the world's physics community, built on half a century of increasingly airtight experiments, honored with science's highest award. It is worth letting the weight of that consensus settle, because in a world full of contested claims and shifting findings, this is something genuinely rare, a profound and counterintuitive result that the entire relevant scientific community regards as settled beyond reasonable doubt. The violation of Bell's inequality has been confirmed not once, but in experiment after experiment by different teams with different particles, different methods, across decades, in laboratories around the world, with every loophole progressively closed. There is no serious scientific dissent about the basic finding. The debate is entirely about how to interpret it, what it means, which assumption to abandon, not about whether local realism has failed. When a result has been tested this thoroughly, replicated this widely, scrutinized this hard, and still stands, it has earned a level of confidence that few claims about the deep nature of reality ever achieve. This is about as certain as our knowledge of the physical world gets, and that certainty is precisely what makes the discovery so remarkable, because the conclusion is so contrary to common sense. It would be one thing to be told a strange story about reality on someone's authority, or as a speculative theory that might or might not be true. It is another thing entirely to know that the strangeness has been forced upon us by the universe itself, demonstrated in experiment after experiment, confirmed to the satisfaction of the most demanding and skeptical community in history. We are not being asked to believe that the world is not locally real as a matter of faith or fashion. We are being shown it by reality through experiments designed to give the comfortable answer every chance to prevail, an answer that never came. The strangeness is not a story we are telling ourselves. It is a fact the universe has insisted upon, against all our hopes and intuitions, and that is what gives it its extraordinary force. The universe, it was now beyond reasonable doubt, does not obey local realism. The deep, common-sense picture of a world made of definite things, sitting in definite states, influencing each other only through signals slower than light, is simply not how reality works. And that leaves us facing a set of possibilities that are, each of them, profoundly strange. So if the universe is not locally real, what is it? Here we have to be careful and precise, because the experiments do not tell us exactly which of our assumptions to abandon. They tell us that we cannot keep them all. Local realism was the combination of two ideas, realism and locality, and the experiments prove that this combination is false. But that leaves us with a genuine choice about which part to give up, and each option is strange in its own profound way. The first option is to give up realism, to accept that particles genuinely do not have definite properties until they are measured. In this view, Einstein was wrong, and the quantum theory was right all along. Before measurement, a particle truly does not possess a definite value for the property being measured. It exists in a haze of possibilities, and the definite value comes into being only when the measurement occurs. The coin in the drawer at the quantum level is not secretly heads or tails. It is genuinely in an indefinite state, neither and both, until something measures it. This is a staggering thing to accept, because the definiteness we take for granted, the sense that things have definite properties, whether or not we look, is simply not true at the foundation of reality. The properties are not there, waiting to be found. They are brought into definite being by measurement. Sit with how radical this first option really is, because it overturns something we never even thought to question. It means that, at the deepest level, the world is not made of little things with definite properties, like tiny marbles, each with a fixed color and position. It means that the properties themselves, the very attributes we think of as belonging to things, do not have definite values until the moment of measurement. That reality, at its base, is a realm of genuine potential rather than fixed fact, a haze of what could be that resolves into what is only through the act of measurement. The solidity and definiteness we see all around us would then be something that emerges through the constant measuring that all the particles of the world perform on one another, not a property that the particles possess on their own. Definiteness in this view is not the starting point of reality, but a product of it, something that happens rather than something that simply is. And yet, strange as this is, many physicists find it the more palatable of the two options, because it preserves locality, the cherished principle that nothing influences anything faster than light. If we accept that particles simply do not have definite values until measured, then we do not need any spooky instant connection across space. The correlations of entanglement arise not from a signal passing between the particles, but from the deep way the entangled system is structured as a single whole. This is the direction many working physicists lean, giving up the assumption of definite pre-existing properties while holding on to locality. But it comes at the price of accepting that the bedrock definiteness of the world, the sense that things are just there, with their properties fixed, is an illusion of scale, true enough for cups and tables, but false for the particles beneath them. The second option is to give up locality, to accept that there really are influences or connections that ignore distance, that link entangled particles instantly across any separation, faster than light, exactly the spooky action, at a distance that Einstein found so unacceptable. In this view, the particles might have definite properties after all. But they are connected by something that does not respect the limits of space and the speed of light, some deep linkage that ties distant parts of reality together instantaneously. This too is staggering, because it means the comfortable picture of a world where things only affect their immediate neighbors, where influences travel sensibly across space at limited speed, is false, replaced by a reality woven together by connections that span any distance in an instant. Sit with this second option for a moment as well, because it is every bit as profound as the first and in some ways even harder to accept. It would mean that the universe is, at its foundation, deeply connected, that the separateness we perceive, the sense that distant things are truly independent, isolated by the vast empty space between them, is in some sense an illusion. Beneath the apparent separation, entangled particles would remain bound in a single connected whole, their fates linked across any gulf of space, as though distance itself were not the absolute barrier we take it to be. It is a vision of a universe that is, at its base, one interconnected thing, its parts joined by relationships that ignore the separations we consider so fundamental. To accept this is to accept that the deepest structure of reality is not a collection of independent pieces scattered across space, but a unified web in which distant things can be intimately, instantly linked. It is important to add, immediately, that even this non-local connection cannot be used to send any signal or message faster than light, as we will discuss, so it does not overturn the cosmic speed limit for information or open the door to the paradox that true faster-than-light communication would bring. The connection is real but subtle, a correlation rather than a controllable influence, something that links the outcomes of measurements without allowing anything to be transmitted through it. So this option does not return us to a world of science fiction instant communication. It returns us, instead, to a world that is quietly, deeply interconnected at its foundation, in a way that defies our sense of distance and separation, while still respecting the limits on what can actually be sent from place to place. Either way, whether we give up definite properties or give up strict separation, the world is revealed to be profoundly stranger than the tidy, separate, definite picture we began with. And there are views that give up both, or that reframe the whole question in subtle ways. But the inescapable core of it, the thing the experiments establish beyond doubt, is that at least one of these deeply held, common-sense assumptions must be wrong. Either things do not have definite properties until measured, or reality is connected across distance in ways that defy speed of light, or both. There is no way to keep the cozy, intuitive picture intact. The world, at its foundation, is one of these strange things, and we do not get to choose the comfortable option, because there is no comfortable option left. Whichever way you turn, reality is revealed to be far stranger than the solid, definite, sensibly connected world our intuitions insist upon. The most basic assumption we make about the nature of things, that they are simply there, definite and independent, influencing each other only through ordinary local means, has been shown by experiment to be, in one way or another, false. It is worth pausing to absorb just how unusual it is for science to overturn an assumption this deep. Most scientific discoveries, even the great ones, operate within a shared framework of basic concepts. They tell us new things about a world whose fundamental categories we still trust. But the failure of local realisms strikes at the categories themselves, at the very ideas of definite properties and local influence that we use to think about anything physical at all. It is not telling us that the world contains some surprising new object or force. It is telling us that the basic way we conceive of objects and their relationships is, at the foundation, mistaken. That is a far rarer and more disorienting kind of result, and it is why this discovery occupies such a special place, why it provokes such vertigo, and why it took the combined genius of Einstein, Bohr, Bell, and decades of experimentalists even to formulate and settle it. And it is why, even now, the full meaning of the discovery is still being absorbed, not just by the public, but by physicists themselves. To accept that local realism is false is easy enough to state in a sentence, but to truly rebuild one's intuitions around it, to develop a genuine feel for what a non-locally real world is actually like, is the work of a lifetime and arguably the work of generations. We are, in a real sense, still learning how to think about a universe that does not obey the assumptions we evolved to take for granted. The equations work perfectly. The predictions are confirmed to staggering precision. The experiments are beyond dispute, but the deep conceptual digestion of what it all means, the construction of a new and accurate intuition about the nature of reality, is an ongoing project, one of the great unfinished tasks at the foundations of physics, and one that makes this an extraordinary moment to be alive and paying attention. Now we arrive at the point where care matters most, because this discovery is one of the most misunderstood in all of science, and the misunderstandings can transform from a profound truth into a source of needless dread. So let us be very clear about what this does not mean, because the false versions are everywhere, and they are frightening in a way the real discovery is not. First and most important, this does not mean that nothing is real. You will hear people say that the experiments prove reality is an illusion, that nothing exists, that the world is a dream. This is simply wrong. The discovery is about local realism, a specific technical combination of assumptions, not about whether reality exists at all. The world is still here. You are still here. The cup on the table is a real cup. What the experiments overturn is the assumption that particles carry definite values for every property, whether or not they are measured, and the assumption that influences are always local. To give up those specific assumptions is a profound thing, but it is worlds away from saying nothing is real. Reality is still entirely real. It is simply real in a way that is stranger and subtler than our common sense picture assumed. Second, this does not mean that human consciousness creates reality, that the universe needs a mind to look at it before things become definite. This is a particularly seductive misreading, the idea that your awareness, your attention, somehow conjures the world into being. But remember what measurement actually means in physics. A physical interaction, an event in which a quantum system interacts with a larger system, a detector or the environment, producing a definite outcome. This happens whether or not any conscious being is present. The measuring device does not need a person watching it. The interaction itself is what matters. Reality does not wait for human minds. The universe was producing definite outcomes through physical interactions for billions of years before there were any conscious observers at all. The discovery says nothing about consciousness having magical powers over reality. It is about the physics of measurement and interaction, full stop. This point deserves real emphasis because the idea that the mind creates reality is one of the most common and most misleading things people take away from quantum physics, and it simply does not follow from the experiments. The confusion comes from the word observer, which in physics is a technical term for any system that performs a measurement, a detector, an instrument, a stray particle of the environment, not specifically a conscious mind. When a quantum system interacts with a large measuring apparatus, a definite outcome is recorded, and this happens entirely through physical processes, with no need for anyone to be aware of it. A detector left running alone in a sealed, dark laboratory records definite outcomes all night long, whether or not a single human being ever looks at the results. The universe does not check whether anyone is paying attention before it behaves. The role of measurement in quantum mechanics is a role played by physical interaction, not by awareness, and reading it as a claim about the power of the human mind is a misunderstanding, however poetic and tempting that misunderstanding may be. It matters to get this right, not only for accuracy, but for peace of mind, because the false version, the idea that reality is somehow conjured by observation, can be genuinely disturbing, can make the world feel unstable, dependent on being watched, liable to dissolve the moment attention turns away. The true picture is far more reassuring. The world is robustly, independently real. It goes about its business of interaction and measurement constantly, everywhere, with or without witnesses, producing the solid, definite reality we inhabit through physical processes that have nothing to do with whether anyone is looking. You do not hold the world together by observing it. It holds itself together through the ceaseless interactions of all its parts, and it would carry on doing so perfectly well if every conscious being vanished tomorrow. The strangeness the experiments reveal is real, but it is not the strangeness of a world that needs your attention to exist. Third, this does not mean we can send messages faster than light, or use the spooky connection of entanglement to communicate instantly across space. This is perhaps surprising, but it is firmly established. Even though entangled particles show these strange correlations across any distance, the outcomes at each end are individually random, and you cannot use them to actually transmit information faster than light. There is a deep principle, well understood and proven, that prevents the strangeness of entanglement from being used for faster-than-light communication. So, whatever the connection between entangled particles is, it cannot be harnessed to send a signal, cannot be used to break the cosmic speed limit for information. The spookiness is real, but it is subtle, and it does not open the door to instant messaging across the galaxy or any of the science fiction possibilities people sometimes imagine. So strip away the misunderstandings, and what remains is both more modest and more profound than the wild versions. The world is real. Your mind does not conjure it. No one can send signals faster than light. And yet, beneath all of that, the experiments have shown that reality, at its foundation, does not work the way common sense insists, that the assumption of definite properties existing independently of measurement, combined with strictly local influences, is false. The truth is not that nothing is real, but that reality is woven together, in a way far stranger and more wonderful than the solid, definite, sensibly connected world we imagined, a way we are still, even now, struggling fully to comprehend. There is a deeply human story woven through all of this, a story of one of the great intellectual dramas of the 20th century. And it is worth telling because it reveals something beautiful about how science confronts even its most cherished assumptions. At its heart was a disagreement between two of the greatest physicists who ever lived, Albert Einstein and Niels Bohr, who argued for years about the nature of quantum reality. Bohr embraced the strange new quantum picture, the indefiniteness, the role of measurement. Einstein resisted it with all his considerable genius, convinced that the universe must be more sensible underneath, that there must be a deeper, definite reality that quantum mechanics was failing to capture. Their debate was legendary, carried out in papers and lectures and conversations, two titans of physics disagreeing about the very nature of the world. And when Einstein died, the argument was still unresolved, still seemingly a matter of philosophy, with no way to tell who was right. Their debate has become one of the legendary episodes in the history of science, a clash between two of its greatest figures over the deepest question of all: what is the world really like? It was not a hostile feud, but a profound and respectful disagreement between people who admired each other enormously, which somehow makes it more poignant. At the great physics gatherings of their era, Einstein would arrive with some new thought experiment designed to expose a flaw in the quantum picture, some clever scenario meant to show that it led to absurdity or contradiction. And Bohr would take it away, wrestle with it, and return with a response showing that the quantum theory survived after all. Again and again this happened, Einstein probing, Bohr defending, the two of them circling the same deep question for years, each forcing the other to think more deeply, neither able to land the decisive blow. It was a contest of titans over the nature of reality itself, conducted with brilliance and mutual respect, and it captivated the world of physics for decades. And yet, for all its brilliance, the debate could not be settled, because it remained at bottom a disagreement about how to interpret a theory that both men agreed made correct predictions. They were not arguing about what the experiments showed. They were arguing about what the experiments meant, about the reality beneath the equations, and that was precisely the kind of question that seemed to lie beyond the reach of any experiment to decide. So the greatest scientific debate of its age ended not in resolution but in stalemate, with Einstein going to his grave still convinced that the quantum theory must be incomplete, still believing in a deeper, definite reality, and with no way for anyone to prove him right or wrong. It seemed that the question might remain forever in this suspended state, a matter of taste and intuition, a thing reasonable people could disagree about endlessly. That it did not remain so, that the question was eventually pulled down from the realm of philosophy and settled in the laboratory, is one of the most surprising and wonderful turns in the whole history of science. Then came John Bell, a physicist who, remarkably, worked on this question almost as a side passion, a deep personal fascination, while doing other work to earn his living. Bell was, in a sense, sympathetic to Einstein. He found the quantum picture troubling and was drawn to the hope that a deeper, more sensible reality might underlie it. And yet it was Bell who, with rigorous honesty, found the way to test the question, and whose test would ultimately show that Einstein's hoped-for local realism could not be saved. There is something profoundly admirable in that, a scientist following the logic to a conclusion he might not have wished for, building the very tool that would overturn the picture he found most comfortable. Bell did not set out to prove Einstein wrong. He set out to clarify the question, to turn a philosophical dispute into something precise and testable, and he succeeded so completely that the universe itself could be made to answer. And then came the experimentalists, the patient, ingenious physicists who spent careers building the delicate apparatus needed to actually perform Bell's test, to generate entangled particles, measure them along carefully chosen angles, and tease out the correlations from the noise. Clauser, working with crude early equipment, and skepticism from some colleagues who thought the question pointless. Aspect, devising clever ways to change the measurement settings in flight and close the communication loophole. Zeilinger and others, pushing the experiments to ever greater rigor and distance, sealing off every escape route for local realism. It was decades of careful, demanding, often underappreciated work, the slow conversion of Bell's brilliant idea into hard experimental fact, and it culminated in the Nobel Prize that recognized what they had accomplished, the experimental settling of one of the deepest questions about the nature of reality. It is a story that captures something essential about science, the way it refuses to leave even the most fundamental assumptions unexamined, the way it finds methods to test what seemed untestable, the way it follows the evidence even when the evidence overturns the views of its greatest figures. Einstein was perhaps the most brilliant physicist who ever lived, and on this question the evidence shows his intuition was wrong, and science accepted that because science answers to experiment, not to authority. Not even to the authority of an Einstein. The universe was put to the question, and it gave its answer, and the answer was stranger than even the boldest of the founders had been willing to believe. There is a kind of grandeur in that, in a species capable of setting aside its most cherished common sense and its greatest authorities to follow the universe's own testimony wherever it leads. It is worth pausing, too, on the strange and beautiful fact that this entire drama played out over the better part of a century, across generations of physicists, as a single, continuous conversation with reality. Einstein posed his objection in 1935 and died without an answer. Bell found his test in 1964, decades later, building on the unresolved argument of those who came before. The experimentalists then spent another half-century turning Bell's idea into ever more refined reality, each generation handing the question to the next, until the loophole-free tests and the Nobel Prize finally closed the matter. No single person could have done it. It required a relay of minds across time, each contributing a piece, the question outliving the individuals who asked it, carried forward by the collective enterprise of science until it was answered. There is something moving in that image of a question too deep for any one lifetime, passed from hand to hand across the decades, until at last the universe was made to speak, and the answer it gave was not the comfortable one. It would have been easier, in a sense, if the experiments had confirmed local realism, if Einstein's sensible picture had prevailed, if the world had turned out to be the definite, locally connected place common sense demands. Science would have been spared a great deal of puzzlement, but the universe did not give the comfortable answer, and science did not flinch from the uncomfortable one. This is perhaps the deepest lesson of the whole story, deeper even than the strange truth it revealed, that the enterprise of understanding the world is willing to follow the evidence, past the limits of common sense, past the authority of its greatest figures, past the boundary of what feels possible, into whatever strange territory the universe actually occupies. That willingness is what allowed us to discover something so contrary to intuition, and it is one of the noblest features of the human mind. Let us step back now from the experiments and the history and simply sit with the wonder of what has been discovered, because once the fear of misunderstanding is set aside, what remains is genuinely awe-inspiring. We have learned, through careful experiment, that the universe is stranger at its foundation than our deepest common sense ever allowed. The world that feels so solid and definite and sensibly connected rests at its base on something that defies our most basic intuitions, a reality where definiteness may emerge only through measurement, or where distant things are linked in ways that ignore the vast space between them. The cozy picture we are born believing, the picture of definite objects sitting in definite states, turns out to be a kind of useful approximation, a surface appearance, beneath which lies something far more subtle and profound. And there is a particular wonder in how we came to know this. We did not learn it by accepting anyone's authority, or by philosophical argument, or by intuition. We learned it by asking the universe directly, by devising an experiment so clever that reality itself was forced to reveal which of our assumptions was false. Think about that achievement. A question about the deepest nature of reality, whether things are definitely there when we do not look, a question that seemed to belong forever to philosophy, was turned through human ingenuity into a measurement, a number, a thing the universe could be made to answer. We found a way to interrogate existence itself, and existence answered. That we are capable of this, that a species of curious creatures on a small planet can pose such a question to the cosmos and receive a clear reply, is one of the most remarkable things about us, and about the universe that permits itself to be questioned in this way. The strangeness, properly understood, is not a threat but an enlargement, an expansion of our sense of what reality is. We thought the world was simple at its base, made of definite things behaving sensibly. We have discovered it is profound at its base, woven together in ways that strain our comprehension, richer and subtler and more mysterious than we imagined. This is not a loss, it is a gift. It means we live in a universe far more interesting than the one common sense describes, a universe whose foundations hold genuine mystery, whose deepest nature is still being explored, whose reality is more wonderful than the flat, obvious picture we started with. To learn that the world is stranger than you thought is not to lose the world. It is to discover that it was always more than you knew. There is a special quality to this particular strangeness, too, that sets it apart from other astonishing discoveries in physics. When we learned how vast the universe is, or how old, or how tiny the atoms are, We were learning surprising facts about a world whose basic character we still understood. But the failure of local realism is different. It is not a surprising fact about the world, so much as a revision of what kind of thing the world fundamentally is. It reaches beneath the facts to the very framework, telling us that the categories we use to think about reality, definite properties, local influences, things being simply there, do not apply at the foundation in the way we assumed. This is a rarer and deeper kind of discovery, the kind that does not just add to our knowledge, but reshapes the container that holds it. And there have been only a handful of such moments in the entire history of science. To have lived to learn of one of them, to be able to hold it in your mind, is a quiet privilege. And it leaves us in a fascinating position, because the question of which assumption to abandon, and exactly what reality is like beneath the surface, remains genuinely open and actively debated among the people who understand it best. The experiments settled that local realism is false, but they did not settle what to put in its place. Physicists continue to explore the different possibilities, to develop and argue over the various ways of understanding what the failure of local realism truly tells us about the world. So, we are not at the end of this story, but in the middle of it, living through an ongoing investigation into the deepest nature of reality, with the central fact established and its full meaning still being worked out. There is something thrilling in that, in knowing that the question of what the world is, at its very foundation, is not a closed book but a live and unfolding inquiry, and that we are here to witness it. And there is something freeing in it too. The common-sense picture of reality, for all its comfort, was a kind of cage, a set of assumptions we mistook for necessities, a conviction that the world had to be a certain way. The discovery that the universe is not locally real breaks that cage open, reveals that reality is not bound by our intuitions, that it is free to be far stranger and more wonderful than we assumed it had to be. The world is not obligated to match our common sense. It never was. And in discovering that, we are invited into a larger reality, one whose true nature we are still uncovering, one that has already shown us it can surprise us at the deepest level, one that holds, no doubt, further wonders we have not yet learned how to ask about. That is not a frightening prospect. It is an exhilarating one. And consider what it says about us, about the kind of creature capable of discovering such a thing. We are made of the very particles whose behavior defies local realism, assembled out of the strange quantum foundation we have been describing. And yet, from within that reality, we have managed to turn around and examine it, to ask it the deepest questions about its own nature, and to devise ways of making it answer. There is something almost miraculous in that, in a part of the universe becoming aware enough, curious enough, ingenious enough to investigate the rules of the whole. The same reality that is not locally real has produced in us beings who can discover that it is not locally real. The cosmos has, in a sense, used us to come to know one of the deepest truths about itself, and that is a strange and beautiful kind of participation in the very mystery we are studying. This is perhaps the deepest source of awe in the whole story, deeper even than the strangeness of the discovery itself, that the discovery was possible at all, that the universe is the kind of place that can be understood, at least in part, by the creatures within it, and that those creatures are the kind of thing that wants to understand. There was no guarantee of either. The world might have been forever opaque to us, its deepest nature permanently hidden, or we might have been incapable of or uninterested in probing it. Instead, Reality turned out to be intelligible, and we turned out to be curious. And the meeting of those two facts has allowed us to reach all the way down to the foundations of existence and learn that they are stranger than we ever imagined. To be a part of that, to live as one of the curious fragments of a comprehensible universe, is a privilege almost too large to take in, and it transforms the strangeness of the discovery from something frightening into something to be deeply grateful for. What does it mean, then, for you going about your life in a world that's been proven not to be locally real? The remarkable and reassuring answer is that, at the level you live, it changes nothing about the solidity and reliability of your world, and yet it quietly deepens everything. The strangeness lives at the level of individual particles, in the delicate correlations of entanglement, in the haze of indefiniteness before measurement. By the time you assemble countless particles into a cup, a table, a hand, a world, all that delicate quantum strangeness has, through the constant interactions of everything with everything, settled into the solid, definite, dependable reality you experience. The cup really is on the table. Your hand really is your hand. The world really is there when you turn away. The quantum strangeness does not bubble up to make your everyday world uncertain. It remains at the foundation, supporting a reality that, at human scale, is exactly as solid and trustworthy as it has always been. So you can hold both truths at once without conflict. The world you live in is real, solid, definite, and reliable, and you can trust it completely. Lean on it, build your life in it, exactly as you always have. And, at the very same time, you can know that beneath that solid surface, at the level of the smallest things, reality is woven together in a way that defies common sense, a way that the deepest experiments have revealed and that we are still working to understand. These do not contradict each other. The solid world is the large-scale face of the strange foundation. The way a smooth, dependable image on a screen is made of countless flickering pixels you never notice. You live on the smooth surface, and you can trust it, while knowing that underneath lies something stranger and more wonderful than the surface reveals. The reason the strangeness stays safely at the bottom and does not rise up to make your daily life uncertain is itself worth understanding, because it is what makes the whole picture livable. The delicate quantum features, the superpositions, the entanglements, the indefiniteness are extraordinarily fragile. The moment a quantum system interacts with its surroundings, with the countless particles of the air, the light, the warmth of the everyday world, those delicate features are washed out, and the system settles into the definite behavior we are used to. This is why we have to work so hard in special laboratories, with isolated particles and careful shielding, even to observe the quantum strangeness at all. In the ordinary world, it is constantly being erased by the relentless interaction of everything with everything. By the time you reach the scale of objects you can see and touch, the strangeness has been thoroughly smoothed away, leaving the solid, definite, dependable world of experience. The quantum foundation is real, but the everyday world is just as real, and the bridge between them is this constant washing out of the delicate quantum features by the busy interactions of the large-scale world. So there is no danger that the failure of local realism will somehow leak into your kitchen and make your coffee cup flicker between existence and non-existence, or that your keys will dissolve into a haze of possibilities when you set them down. The scale of your life is far too large, far too warm, far too thoroughly interconnected for that. The strangeness is sealed at the bottom. In the realm of the isolated and the tiny, and the world you actually inhabit is as solid and reliable as it ever was, built upon that strange foundation, but not destabilized by it. You can hold the profound truth in your mind that reality is not locally real at its base, and lose not 1 ounce of trust in the dependable world around you, because the two belong to different scales, and the strangeness of the one does not undermine the solidity of the other. There is something quietly marvelous in carrying this knowledge through an ordinary day. You pick up a cup, and you know that the particles composing it are governed by rules that defy local realism, that at their foundation they are part of a reality far stranger than the simple solid object in your hand suggests. You watch light fall through a window, and you know that the photons carrying that light can be entangled across vast distances, linked in ways that ignore the space between them. The ordinary world, fully real and fully trustworthy, is also, at its foundation, a place of genuine and proven mystery. And to know this is to walk through your days with a kind of doubled awareness, the comfort of the solid surface and the wonder of the strange depths, held together, each enriching the other, and none of it asks anything of you or threatens anything you care about. The people you love are real, and your love for them is real, and nothing about the failure of local realism touches that in the slightest. The beauty of the world is real. The warmth of an ordinary moment is real. The discovery operates at a level so far beneath the texture of human life that it leaves everything you actually care about completely intact, untouched, fully present. It does not reach up to diminish your world. It only reveals, far below, a foundation more wonderful and mysterious than you knew. You can receive that as a gift, a deepening of the ordinary, an invitation to feel wonder at the strange reality underlying your perfectly solid and dependable life, and then you can return your full attention to that life, which is waiting for you exactly as it always was, real and warm and yours. It can even, if you let it, lend a quiet richness to the most ordinary experiences. Hold a cup of something warm, and you might reflect that the particles in your hand and the particles in the cup are, at their foundation, part of a reality that defies the simple separateness we perceive, bound into the same strange quantum fabric as everything else. Look at a person you love across a room, and you might sense, beneath the ordinary scene, the deep and proven mystery of a world that is not locally real. A world in which the tidy separations and definite properties we take for granted are, at the deepest level, not the whole story. None of this changes the warmth of the cup or the love in the room. Those remain exactly as real and as precious as ever. But the knowledge adds a layer, a quiet undertone of wonder, a sense that even the most familiar moment is set against a backdrop of genuine and beautiful mystery, that the ordinary world is shot through, all the way down, with something extraordinary. And perhaps that is the truest gift of a discovery like this, not the specific physics, which most of us will never use, but the way it transforms our relationship to the ordinary world, restoring to it a sense of depth and mystery that familiarity had worn away. We grow so accustomed to the world that we stop seeing it, stop marveling at it, treat it as a flat and obvious backdrop to our concerns. A discovery like the failure of local realism cuts through that familiarity, reminds us that the world we think we know so well is, at its foundation, profoundly strange and not yet fully understood, that the ground of our ordinary existence is one of the great mysteries of science. To carry that awareness is to live in a slightly enchanted world, a world whose ordinary surfaces conceal extraordinary depths, and that is a richer way to live than taking the world for granted. a way of moving through your days with a quiet, steady sense of wonder at the sheer strangeness underlying it all. It is fitting that thoughts like these settle most deeply in the quiet of the night, when the busyness of the day falls away and the mind has room to drift out toward the deepest questions about the nature of things. In the daylight, surrounded by the obvious solidity of the world, the idea that reality is not locally real seems almost impossible to take seriously, too strange to be true. But at night, in the stillness, the ordinary certainties loosen a little, and it becomes possible to feel the genuine mystery that the experiments have revealed, to sense, just beneath the solid surface of the world, the strange and wonderful foundation that physics has uncovered. The night is when the great questions breathe, when the mind can hold the possibility that reality is far stranger than it appears, and find in that possibility not fear, but a quiet, expansive wonder. And there is particular gentleness in approaching this discovery at the end of the day, when you are not trying to do anything with it, not trying to use it, or apply it, or even fully grasp it, but only to let it be, to let it expand your sense of the world a little before you sleep. You do not need to understand the mathematics, or resolve which assumption to abandon, or settle the debates that still occupy the physicists. You need only to hold lightly the simple and astonishing fact that the world has been shown to be deeper and stranger than common sense allows, that the solid reality around you rests on a foundation that defies our most basic intuitions, and that this was discovered not by guesswork, but by patiently asking the universe itself. To hold that thought gently, without strain, is enough. It asks nothing of you but a moment's wonder, and wonder in the end is the right note to rest on, because this discovery, rightly understood, is one of the great wonders that science has uncovered, fit to sit alongside the vastness of the cosmos and the depth of time, and all the other marvels that expand our sense of the reality we are part of. It is the kind of thing that, once known, quietly enriches the texture of existence, so that an ordinary evening, an ordinary room, an ordinary moment of rest carries within it the knowledge that the foundation of all of it is a proven and beautiful mystery. You are not living in a flat and obvious world. You are living in a world whose deepest nature is genuinely astonishing, and you can let that knowledge settle over the night like a soft and pleasant weight, a reminder of how much more there is to reality than meets the eye. So as the night deepens around you, let yourself rest in the strangeness gently, without any need to resolve it or fear it. Somewhere beneath the level of your senses, at the scale of the smallest things, reality is woven together in a way that defies the common sense we are all born with, a way proven by careful experiment and honored by the highest awards in science. You will never see it directly. It does not disturb the solid world you live in, but it is there, the strange and beautiful foundation of everything, the proven fact that the universe is not the simple, definite, locally connected place it appears to be. And you are part of that universe, made of the very particles whose behavior defies local realism, a real and solid being resting on a foundation of genuine mystery. There is nothing in that to fear. There is only the wonder of being part of a reality so much deeper and stranger than it seems. Let the solidity of your world hold you as it always has. The bed beneath you is real and holds your weight. The room around you is real and definite and there. And it will still be there when you close your eyes, whether or not anyone is looking. Because at the scale of beds and rooms, the world is solid and dependable and trustworthy, exactly as it has always been. The strangeness lives far below, at the level of single particles, and it does not reach up to unsettle the comfortable reality you rest in. You can trust the world completely, lean into it fully, precisely because it is real. Whatever subtle and wonderful strangeness lies at its foundation. The deep mystery is not a threat to your solid world. It is the marvelous thing that underlies it, the strange and beautiful base on which your dependable reality is built. There is a profound peace available in that, the peace of trusting the world while remaining open to its mystery. You do not have to choose between the solid reality you live in and the deep strangeness physics has revealed beneath it. You can have both, holding the everyday world close and trusted while letting the deeper mystery be a distant, gentle wonder, a thing you know is there, without needing to grasp it fully or fear it at all. This is, in the end, a comfortable way to live with one of the strangest truths science has ever uncovered, to keep your world exactly as real and solid as it has always been, and to let the deep strangeness rest quietly underneath, supporting it. A proven and beautiful mystery you can marvel at in the quiet hours and then set gently aside, returning always to the warm, real, dependable life that is and remains entirely yours. So let your thoughts slow now, and let the great strangeness settle into the quiet of the night. You have traveled, tonight, to one of the deepest questions there is. The question of whether the world is simply, definitely there when no one looks. And you have seen that the answer, delivered by experiment and honored with the highest prize in science, is stranger than common sense could ever have guessed. The universe is not locally real. Either things do not have definite properties until they are measured, or reality is connected across distance in ways that defy the speed of light, or both. The solid, definite, sensibly connected world we are all born believing in turns out to be a surface, beneath which lies something far more subtle and profound. And you have held that idea and looked at it, and seen both its vertigo and its wonder, and learned what it does and does not mean. Picture it one last time softly, without fear. The world all around you, solid and real and dependable, exactly as present as it has always been. And beneath it, at the scale of the smallest things, a foundation of proven mystery, a reality woven together in ways that defy our deepest intuitions, where definiteness may bloom only through measurement, where distant particles are linked across the void. The world is real, you are real, and underneath there lies a mystery more profound than common sense. Allows, supporting everything, asking nothing of you, simply being the strange and beautiful truth of the reality you are part of. There is nothing you need to do with this knowledge tonight. The physicists will go on probing the foundations of reality, refining the experiments, exploring what it means that the universe is not locally real, working at the frontier of the deepest questions there are. The strange foundation will go on supporting the solid world, silent and unseen, as it always has. And you can simply let it all be, the solid surface and the strange depths, the real world and its mysterious base, and turn toward rest, a real being in a real world, carrying now a little of the wonder of having glimpsed how strange that real world is underneath. Let the room around you be both completely real and profoundly mysterious, and let that be enough without needing to resolve it, without any trace of fear. You are here, whole and real, resting in a world you can trust, a world that will still be there when you close your eyes, beneath which lies one of the most beautiful and surprising truths science has ever uncovered. And that is a good thing to know as you drift towards sleep. Not a thing to fear, but a thing to wonder at. The gentle and astonishing fact that the solid world you live in is the surface of something deeper, that reality is richer and stranger than it seems, and that you are a real and remarkable part of it, now and through the whole of the quiet night, exactly as you always have been, resting solid and real, and at peace on the strange and beautiful foundation of all things.